Here is a quick reminder and explanation of bounds. To determine the upper bound, take the rounding accuracy and add half of it to the measurement. For example, if rounded to the nearest meter, add 0.5 meters. For the lower bound, subtract half of the rounding accuracy. For instance, if rounded to the nearest meter, subtract 0.5 meters. So, if the measurement is 3 meters rounded to the nearest meter, the upper bound is 3.5 meters, and the lower bound is 2.5 meters. In this session, we'll be reviewing the importance of accuracy in rate calculations and measurements. Specifically, we'll be exploring how to determine upper and lower limits to ensure accurate and reliable result ranges are fully understood. Let's start by understanding why upper and lower limits are crucial in rate calculations and measurements. Whether you're working in science, engineering, or any field that involves quantitative analysis, establishing these limits helps us account for uncertainties and variability in our data. Upper and lower limits represent the range within which a measured value is expected to fall. This range is determined by considering the precision and accuracy of our instruments and the inherent variability in the process being measured. Precision is key when working with measurements. Precision refers to the degree of repeatability of a measurement. To establish upper and lower limits, we need to consider the smallest possible difference our instrument can detect reliably. Firstly, identify and quantify the uncertainties associated with your measurement. This could include instrument error, environmental factors, and other sources of variability, including the smallest unit that an instrument might be able to display. Next, consider the precision of your measuring instrument. These examples are simple measuring devices and gauges, and their accuracy is variable. On top of this, human error in reading or working them can occur. Let's go through a quick example to illustrate these steps. Imagine you're measuring the rate of a chemical reaction. Consider the uncertainties in your reaction conditions, the precision of your measuring device, and any systematic errors that might affect your results. Items like measuring cylinders can give accuracy to the nearest milliliter. Some stopwatches might be able to measure to the nearest millisecond, others to the nearest second. The rate of a reaction can be calculated by dividing the change in the amount of reactant or the amount of product produced by the time taken. If we were looking for our fastest or slowest possible rate of reaction, it's not as simple as using both upper or lower bounds. So, if we measured a 5 cm cubed production to the nearest centimeter cube that took 40 seconds to the nearest second, the fastest possible rate of reaction would be the greatest possible production in the least amount of time, so 5.5 divided by 39.5 is 0.14 centimeters cubed per second. Where the slowest rate of reaction would be the least production by the greatest time. 4.5 divided by 40.5 is 0.11 centimeters cubed per second. If it's not clear which to use, work out all possibilities. If you are told an American football field is 4,460 meters squared to the nearest 10 square meters and the width is 49 meters to the nearest meter, Now imagine your question asks you to find the upper and lower bounds of the unknown length. Here is what we need to consider. The longest possible length would be found by dividing the greatest possible area by the smallest possible width. So, we would use 4,465 meters squared divided by 48.5 meters, which is 92.06 meters. The shortest possible length would be found by dividing the smallest possible area by the longest possible width. So this time, we would use 4,455 meters squared divided by 49.5 meters, which is 90 meters.